In this screencast, you will hear a lot of connections with biology and chemistry. You might recall that this particular textbook, probably more recent editions, are used all over the country for people that are in med school or medical technology classes and need a physics background. Lesson 5 is going to be about surface tension, capillary action, viscous fluid flow, diffusion, osmotic pressure, things that hopefully you've heard a little bit about, but will actually apply mathematically. And pardon the coughing again because of a little bit of allergies on a morning screencast. So first of all, let's talk about surface tension. And you may have observed things that are denser than water, yet are able to float on the surface of water. And one of the main reasons when that happens is because of what we call the surface tension of the water. Now imagine over here on the left, we have two water molecules. Water molecule B is at the surface, water molecule A is somewhere underneath the surface. And imagine this water molecule is interacting with all the other water molecules around it in all three dimensions, not just the two that you see in the picture. And it's being tugged on either by using intermolecular forces or just through collisions, all the other water molecules around it. We talk about these intermolecular forces, and if this liquid happened to be water, of course, we would be talking about hydrogen bonds, if you remember what those are from chemistry and biology. Hydrogen bonds are the forces of attraction between molecules that have both hydrogen and either nitrogen, oxygen, or fluorine. So if you just have water, the hydrogens in one water molecule can be attracted to the oxygens on other water molecules because the hydrogen, if I draw the water molecule right here, and you maybe have seen this diagram many times, when we look at the water molecule, we've got these two lone pair electrons. And in these lone pair electrons, this is going to be the negative region of the water molecule, and where the hydrogens are, since their electron that they're sharing with oxygen are right there, and there's the oxygen's electrons, these electrons are between the hydrogen and the oxygen. That leaves this region where the hydrogens are positive. So you basically have a polar molecule, very important word, polar molecule. You have poles. This area is positive, and this area up here is negative. And so think about a water molecule as being a little mini magnet with a positive and a negative pole, or a north pole and a south pole, if you wish. And that means that all the water molecules can attract other water molecules or other polar molecules, such as ammonia, for example, or compounds that have fluorine in them. We'll pick a simple one like hydrogen fluoride, and that's how we get these hydrogen bonds. So all of the tugs and pulls on water molecule A over here are all around it in 3 dimensions. But up here at the top, there are basically no, or there are at least insignificant tugs and pulls on the water molecule from above. All the tugs and pulls are from the sides and below. And that's what creates this surface tension along the side. There is nothing counterbalancing the downward pull because there are no forces acting upward of any note. So we have this surface tension across the surface of the water. It's almost like a thin film or membrane, though not obviously as dense as the thin film or membrane would be, but it sort of acts like it. And consequently, you can have insects that can be on this, walking across the surface of the water, and leaves can float on the surface of water. Here you have a needle. And so if I make a needle here, and here's the little eye of the needle, and there's the point of the needle there. And then instead of looking at the needle from above or the side, we look at it from the end, where maybe you could have the dot being the point of the needle going into the page, into your iPad, and an X representing, like we did with arrows, the back end of the needle. So the point would be coming out of you, out towards you, and this would be going in from you. And that's what we have in the picture up here. You're looking at the edge, the end, one end or the other of a needle. And it creates this slight depression in the surface of the water. And that slight depression, as you have your force of weight acting down, mg, you're going to have an equal and opposite force, the normal force, acting up. And it's going to be normal to the depression, normal there and normal there to that little depression area. And it's these two vertical components, represented here in red, of that force. And if this is going to be our angle here, or we can call this our theta, this is going to be our normal force pushing out perpendicular to the depression, times the cosine of the angle. And you've got two of them, one from this side and one from that side. So the force of weight acting down is going to equal 2 times the normal force, cosine theta, acting up. And that's the idea of assuming the object is light enough, which means its weight is not that great, even though its density might be greater than water. Its weight that would cause it to sink is counteracted by the surface tension of the water acting upward. And so it looks like it's floating, but it's floating for a different reason, not because its density is less, but because of the surface tension of water. So even though the density of steel is about 8 times that of water, because of the surface tension, it is able to float carefully on that water. Now, if you were to add a little detergent to the water, a little bit of soap, that interferes with the interaction, the hydrogen bonding between all the water molecules. It causes this normal force to be reduced greatly, and then the surface tension, therefore, is much, much less, and then your steel needle or pin will indeed sink. So our surface tension can be represented by this variable right here, gamma. We also use it to talk about gamma rays in other sections of physics. And so what does this surface tension depend upon? It depends upon this force, and it is inversely proportional to the length of the object that is on top of the water. So we know that force is in terms of newtons, and the length is in terms of meters. Therefore, our units are going to be joules per meter squared or newtons per meter. Remember, a newton is a unit of force, which is going to be a kilogram meter per second squared. You can convert newtons per meter into joules per meter squared. And coming down here, this too is because you've got this surface tension acting on both sides of the needle, or in this case, which is an actual device for measuring surface tension, both sides of this curved ring is where the 2 comes from, inside and the outside of the wing, as it creates this depression in the water. And so here's the ring coming through here, and all the way around, it's creating this depression in the water. Another word for soaps or detergents are surfactants, which decrease the surface tension. And that's why we use surfactants, such as soap or detergent, when we wash things, because it enables the cleaning agents to get at soil and blood stains and grass stains and other non-polar substances that are in the cloth or the fabric or on the dishes. This is also very important biologically. If you read through this section, and again, this is an application that is likely not going to be on the AP, not something you'd have to memorize, but it is an extraordinary example of intelligent design, God's genius. And that is that your lungs are filled with these air sacs called alveoli. The surface area of the alveoli in your lungs, if you were to spread out the surface area for millions of alveoli in your lungs, it would actually cover the end zone of a football field. That's an awful lot of surface area across which oxygen and carbon dioxide can diffuse. Oxygen in through the alveoli to your capillaries and your circulatory system, and carbon dioxide out of the capillaries and eventually exhaled. And what's interesting is that your body secretes into the tissue a substance that gradually reduces the surface tension of the liquid. Otherwise, it would be very, very difficult for you to breathe because of the surface tension. And imagine trying to think of some purely accidental Darwinian evolutionary step-by-step process based on mutations that can create this substance and create this presence with your alveoli in your lungs. The better explanation is your lungs were designed this way. So here's an example of the leg of a water strider, which is right here. And that's walking on the surface of the water. You can see the depressions in all 6 of the legs of this insect. Insects have 6 legs, 3 pairs. And it's walking on water, meaning it's not sinking, because every one of those places creates this little depression. And you've got this normal force acting there, and this normal force acting there. And of course, you've got the weight of the insect acting down. And because of the upward forces representing the vertical components of these 2 normal forces, when those 2 forces are equal and the insect is at equilibrium, then it's able not to sink and, of course, not to fly and be pushed into the air. So if the insect's mass is 2 times 10 to the minus 5th kilograms, and the radius of each foot is given right there, we can find that angle theta of the normal force, this vector representing all of the pushes all along the depression. And we're going to just look at one leg, so we're going to be talking, we only need 1/6 of the insect's weight. And the length is going to be the circle where the leg of the insect is pushing down in. That circle depression. The circle depression's up here. And so this is going to be a matter where we plug in our numbers. The first thing we're going to do is find the area. There's the circumference, not the area of that circle, the circumference of that circle. That's going to be our letter L. And we've moved gamma to one side, and we've moved the F to the other side of this equation. When we start off with this equation here, gamma equals F over L. And we've multiplied both sides by L to get the equation. We plug in our numbers. We want to keep track of our units. If you were given this on a test, I bet you the mass of the insect would be in grams, not kilograms, and you'd be expected to be able to convert it. I would not be surprised if the circle was given to you in millimeters, and you'd be expected to put it into meters in order to be consistent with the MKS system, which is essential if you want your force to be in joules. I mean, your energy to be in joules or your force to be in newtons. You have to have your mass in kilograms, and you have to have your length in meters. All right, let's take a look at another phenomenon that you're familiar with, and that is, you know, in chemistry, you've used graduated cylinders before. And here's the base of the graduated cylinder. Graduated, of course, means it's calibrated on the side, maybe in millimeters or something like that. And you should also all know that when you put water in there, you get a little dip, and you always read the height of water in milliliters in your graduated cylinders in the bottom of the meniscus. The word meniscus refers to the bottom. You don't measure it up here. You measure it down there at the bottom of the meniscus. So water adheres to the side, and that's what we would call an adhesive force, because water and glass are made out of different materials, and when you have different materials, the forces of interaction between them are adhesive. If you have water acting on water, for example, in a water drop hanging from a faucet maybe, water molecules acting on water molecules would be cohesive because they're the same. So adhesive is when your forces of interaction are between different molecules, cohesive when they're in the same molecule. Now, by the way, mercury does just the opposite. Mercury bows upward, water bows downward. And all of this is based upon whether or not the adhesive forces are greater than or less than the cohesive forces. So in picture A, the adhesive force is greater than the cohesive force. So the pull of water onto glass is greater than the hydrogen bonding between the water molecules. For mercury, it curves downward because it's just the opposite. The adhesive force between the mercury and the glass is less it's less in strength than the cohesive forces between the mercury molecules. Now you might say, well, mercury molecules, I should say mercury atoms, are all the same. And so whereas in water molecules, you've got these hydrogen bonds, which are pretty significant. But remember that you have what are called London forces, or dispersion interaction forces, or induced dipole forces. And those forces all depend upon how many electrons there are about the atom. And so mercury is quite a big atom. You might recall that mercury is element number 80. And so around each mercury nucleus, you've got 80 electrons. And so it's very likely that as these mercury atoms are moving about and colliding with each other, that they are going to create an uneven distribution of these electrons. And that uneven distribution of electrons is going to create regions of high density and lower density, negative and positive, which creates the London forces, which can be quite substantial for an atom as big as mercury, whereas they are pretty inconsequential when you talk about smaller atoms like hydrogen and helium and so forth. So when we look at the surface of a liquid and the interaction of that liquid with its container, we have to analyze the cohesive forces and the adhesive forces. We can also talk about if you have a drop of water in this case on one kind of surface, such as paraffin, which is nonpolar, and the interaction between water and paraffin is not going to be very great. Water is polar, made out of polar molecules. Paraffin is made out of nonpolar molecules, so they're not going to interact, and so your cohesive forces inside the water molecule are going to be very great, and the water is going to bead up. Think about water falling on a waxed surface of a car after a car wash. Or think about water falling on a windshield that's been coated with one of those sprays made out of some nanoparticles that make it difficult for the water to adhere to the surface of the glass, so it beads up, and you don't need to use your windshield wipers as much. Whereas if you wet the surface, in other words, you put some coating on it, or you remove any debris or any material like paraffin or any of the sprays, then the water can spread out over the surface. And so we can actually measure this angle phi when we draw lines tangent to the surface of the water molecule. And nowadays, more and more, you can actually buy not only sprays to put on the windshield of your car, which I do for my wife on a regular basis when she makes trips down to the Amish market in Farmington, or whenever we go on a trip, we spray this on the windshield so that small rain or misting doesn't make it difficult to drive, and we don't need our windshield wipers as much. But also we're now coating fabric with that. And so the water and other materials sort of bead up on the surface and fall off, and you don't have to wash the clothes as much. So talking about capillary action now. Capillary action refers to something called a capillary. And a capillary is a very, very thin kind of tube. Sometimes that capillary tube might be made out of glass, a glass tube, a man-made tube, which is very, very thin, maybe 100 micrometers right there. Now, biologically, you have blood capillaries, or small vessels through which blood naturally moves. And as the blood goes through those capillaries are so thin, the blood can only go through one red blood cell at a time. They're that thin. And so instead of being 100 micrometers, they are 5 to 12 micrometers. And trees and plants have a vascular system where you have tubes that bring the water and the minerals from the soil up into the plant, called xylem. And you also have phloem tubes, which bring the food, if you will, as the result of photosynthesis, down to the rest of the plant, including the roots. So that would be the phloem, P-H-L-O-E-M. Maybe you studied that in biology. The xylem and phloem tubes make up the capillary system inside plants. So, and those are from 20 to 40 micrometers. Much, much smaller than the ones that we typically use made out of glass, which are 100 micrometers. And again, that's an extraordinary demonstration of intelligent design. A vascular system that is so well designed, water can actually travel many, many meters. Think of a sequoia or a redwood, hundreds of meters up. And of course, it's not just capillary action that does this, but there are many other reasons that enable water to get to the tops of trees, which makes trees possible. The word capillary means hair-like, or about as thin or even thinner as a piece of hair. So, when we take our equation that says this gamma, this surface tension equals the force per length, and then we solve it for force, and we put our 2 pi r in there for the circumference of this capillary tube. And we also have our angle now. We're using phi instead of theta. And as we begin to plug our numbers in, the force of weight, W, is mass times gravity. And instead of talking about mass, you remember that density is mass per unit volume. So therefore, instead of mass, we can use density times volume. And then instead of volume, we can use pi r squared, which is going to be the area of the circle times the height of the circle. And so we get this expression right here, which you've seen earlier in the chapter when we discussed fluids. And so we can have our force acting up, which is our equal the weight, or the force acting down, expressed in these terms, these different terms that we've derived. And we can solve this equation for the height. How high up will this capillary force, if you will, draw through molecular interaction a fluid? And of course, that's going to depend upon a lot of things. It's going to depend upon the density of the fluid. It's going to depend upon the acceleration due to gravity, which on the surface of the Earth is pretty constant. It's going to be concerned with the radius of that capillary action, all of these things. And we can, of course, look that up on a table, these constants. Now, you may have used seen capillary action in action when you go to the doctor or nurse, and they and to get to draw a little bit of blood in order to test your blood, maybe for sugar levels and the presence of other things. They just need a couple of drops now. And so they prick your finger, and a little bead of blood forms on the top of that finger, and you stick your capillary tube, and the blood is drawn up into the tube higher and higher, depending upon how thin that tube is. You can see in the equation down here that as your R gets smaller and smaller, your height, in terms of how high it will go up in the capillary tube, will get higher and higher. I used to have to test my dad's blood all the time for the levels of blood thinner in it. And so I would have to prick his finger with a little device and take a capillary tube that would draw the blood up so that it could be analyzed. Let's see, they mentioned down here plants, depending on capillary action, to bring the water and nutrients up to the rest of the plant. You all know that sponges and paper towels, if you put the edge of them in water, will draw them up. The old commercial of Bounty, the quicker picker upper, drawing maybe you've never seen that commercial. And again, the math is pretty much plug and chug, where if you take the equation for the height that we just derived earlier, and it's a matter of plugging your numbers in, where you can find the newtons per meter capillary force, and you look up your other numbers. There's your gravity, 9.8. Here's the radius, or I should say the radius right here. And there's a lot more than capillary action necessary to get the blood to go way up, not the blood, excuse me, the water and the nutrients and salts to go from the roots of a plant and move all the way up to the top of the plant where the leaves are carrying on photosynthesis. Viscous fluid flow. We had the word viscous in the previous screencast. Viscosity has to do with sort of the thickness or the gooiness, or more technically, the internal friction of a fluid. Water is not very viscous. You do have the hydrogen bonds between the water molecules, which creates some viscosity, but otherwise water is pretty runny, whereas maple syrup and oil and things like that are much more viscous, much stronger internal forces between the molecules, and therefore a greater internal friction. And viscous fluids down here have a tendency to interact with the surface of the container, So the liquid slows down due to that interaction, which we could call friction if you want. Whereas for water, that interaction with the surface is very minimal. And so all the water pretty much goes through very easily if the fluid is non-viscous through your tube, whereas you do get an interaction down here and at the top and all the way around. And so your vectors representing the velocity of the fluid through your tube, it's greater in the middle and not so much at the end. And that's going to slow down the overall fluid flow, which means it's going to require a greater force to push the fluid through the tube. And so when we come over here, here is a very small table showing you the viscosities of a few fluids. Glycerin is a nice thick liquid. Motor oil, which helps to lubricate the pistons moving up and down in cylinders. You can see that those values are very, very high, very, very thick, very, very gooey. You can see that your viscosity changes when you go from 20 degrees to 100 degrees near boiling. You can see that your viscosity, your thickness, is reduced by a factor of more than 3. So the water gets runnier and runnier, if you will, at higher temperatures. And it gets thicker and thicker at cooler temperatures as you approach freezing, but not much cooler. I mean, not much thicker. So we can express all of this in this equation right here. And so we can look at, for example, you would expect that the cross-sectional area, A, is going to be proportional to your force that pushes the fluid through the tube. Obviously, the bigger the diameter, the easier it's going to be for the fluid to go through that tube, and therefore the force is proportional to the area. You also would expect that the greater the force, the faster the fluid is going to go through the tube. That's the velocity. You would also expect that the diameter is going to be a factor, that the bigger the diameter, the less force is going to be required. And you also have your viscosity, which you can pull off a chart. So, I'm sorry, D is the distance, D is not the diameter, D is the distance. I said that incorrectly. So here's your D. And you would expect then that the longer the tube through which the liquid has to go, there's going to be, it's going to affect the ability of the liquid to go through that tube. Now, traditionally or historically, if you go into this in greater detail, instead of being in the MK system with newtons and meters, it's in the CGS system using centimeters, and the unit of force in this case is the dyne and not the newton. And over here, 1 newton is about 100,000 dynes. You won't see the word dyne hardly at all in physics. But if you go into hydraulics, you would come across the dyne in that case. And this is the word poise, named after this guy here, which I believe is pronounced poisai. Poisai, it's French. And so we have Poiseuille's law, which says the rate of flow, which is defined as the change in the volume divided by the change in time, the amount of volume of your fluid going through your tube in a certain amount of time is going to depend upon your change in pressure. Obviously, the greater the difference in pressure from one end of the tube to the other, the greater the difference in pressure, the faster, the more volume is going to be able to be pushed through the tube. So that's in the numerator. You would expect that. The longer the tube, that's going to interfere with the rate of flow because you're going to have more interaction between the flow that's confined to the tube and the more interactions between the material of the flow and the sides of the container. Internal friction, if you want to call it that. It's going to depend upon what is the viscosity of that liquid. Is it runny or is it thick? It's going to depend upon all of these different kinds of things. And I'm looking to see if I've cut, yeah, the radius R, there it is. It's also going to depend upon the radius R. Often we have the lowercase r for that, but using the capital letter R for the radius, and obviously the bigger the tube, if I made my tube a lot bigger, it's going to be easier. And so therefore this is going to be proportional. So you can kind of intuitively derive this equation, though you would not necessarily come up with the number 8, which would come from the calculus. This symbol right here, by the way, is eta in the Greek letter eta. Now back to biology again. The viscosity of your blood is going to depend upon the number of red blood cells. Now, if you have too many red blood cells, if your blood is really thick, it could lend itself easily to creating clots, where the blood is having trouble getting through an artery or a vessel if there's a little bit of plaque, if the blood is too thick. So you might need to have a blood thinner, such as heparin, an anticoagulant, to help make the blood runnier so it can more easily go through the blood vessels. That's something that my dad has to very carefully pay attention to. And that is that flow rate is proportional to the fourth power. And again, the fourth power tells us that when you have a constriction in your vein or your artery, and the blood is trying to get through that vein or artery or capillary, the blood is going to have to work considerably harder to the fourth power to get through. And that's why we pay attention to the thickness of the blood and the and hopefully we pay attention as much as we can determine it, whether or not there's any blockages in the veins or the arteries that can basically cause clots to form or restrictions to blood flow, and that creates all kinds of problems. If the blood has to work, the heart has to work harder to push the blood through, the heart may not be able to work hard enough, and you might have either a heart attack or a inability of the blood to get through, and the blood pressure is going to drop on the far side of the clot, or increase and be very high on the near side of the clot, or the narrowing of the opening. And that's what doctors and nurses have to pay great attention to. Here's a problem having to do with a blood transfusion. You can see the data that's given to you in the problem, the radius of the needle, the length, the density of the blood would be given to you, and it could be measured by other devices. And then your bottle of blood or your bag of blood would be about a ½ meter above the patient's arm so that it's gravity fed. If you imagine the patient with this bag on some type of metal with a hook at the end, and there's the bag hanging over the patient with the tube going down to the patient's arm. And in that bag might be blood, and it might also be aqueous solution containing salts or medicines. In any case, what is the rate of flow through the needle is what this patient is what this problem is asking. So you might remember that your change in pressure is going to be equal to density times gravity times height. You've seen that before. We plug our numbers in to get our change in pressure. We plug the change in pressure here. And now we plug our numbers in. And again, remember, this is to the fourth power. That would have to be given to you. You would not intuitively know it. The same would be true for this constant 8. Here is your viscosity right there. Here is the length of your needle. And when you plug all of your numbers in, it's just a complicated plug and chug problem where you have to do dimensional analysis to make sure that all of your units are consistent with the MKS system. And then you get this answer right here. Reynolds number was mentioned earlier in the chapter. Reynolds number is simply just a way of talking about the streamlined flow or the turbulent flow of a fluid. And it is dependent upon three things: the viscosity, the speed, and in this case, the letter D, which is the diameter of the tube. I said viscosity here. This is the density. There's your viscosity, inversely proportional to that. And this equation would be given to you if you needed it. And we plug in our numbers to get our Reynolds number, named after some guy named Reynolds, who I do not know much about. Sometimes scientists are sort of one and done. They do many, many different things, and they might be famous for just one thing instead of many things. So if the Reynolds number, our benchmark is 2,000. If the Reynolds number is below 2,000, then this fluid is going to be moving in a streamlined fashion. If the Reynolds number gets above 3,000, you're going to have a significant amount of turbulence, which in that case you need to pay attention to that turbulence. And so in this problem, the turbulent flow of blood is again just a plug and chug for turbulence flow. And you would be given not only the formula, but you would be given the values to plug into that formula. And you can see that this would be very, very logical, that your velocity, the speed with which the fluid, the blood in this case, would flow through the tube would be inversely proportional to how long the tube is. So D would go into the diameter. It would be inversely proportional to the thickness, the gooiness of the fluid. The gooier the fluid, the more slowly it's going to flow. So you would expect that also to be, I'm sorry, not the viscosity, but the density would be inversely proportional to that. You would also expect it to be dependent upon the Reynolds number, and which is one value. So all of those things are going to be important in determining the speed with which the fluid is going to go through the tube. Now here's where we move into something you know from chemistry and biology. And imagine we have this imaginary barrier between a fluid or a gas on one side and on the other side. And in fact, this could actually be an actual membrane rather than an imaginary barrier with pores or holes or openings in it. And fluids are always going to go from high concentration to lower concentration much more readily than they're going to go from low concentration to a high concentration. The net effect is going to be a net movement of fluid from left to right until the concentration on both sides is the same. And that's when you're going to reach equilibrium. When you each reach equilibrium, the diffusion from one side to the other will go to zero, and the concentration on both sides of that membrane or throughout the container will be the same. So we can measure the pressure of the place where there's a high concentration on your membrane compared to the place where there's a low concentration. And that difference in concentration will be your pressure difference. And that's going to, if the pressure difference is great, you're going to have rapid diffusion. If the pressure difference is minimal, you're going to have minimal diffusion. And if we're talking about water, we call that diffusion across a differentially permeable or a semi-permeable membrane, osmosis. And oftentimes when we think about osmosis, we think of the movement of gases like oxygen from one place to another. And so as you might expect, your diffusion rate is going to depend upon your change, your difference in concentration. That's going to be proportional. The bigger the difference, the faster the rate. And it's going to depend upon the length that it has to travel through. If it's a long distance or a thick membrane, that's going to slow it down. So diffusion rate is inversely proportional to the length, as you might expect. So this entire equation then is called Fick's law. And the cross-sectional area is going to make it easier for the stuff to diffuse from one place to another, from high concentration to low concentration. And then D is our proportionality constant. It does not stand for density. It's a proportionality constant that depends upon various things such as the units that you're using in the equation. Again, you'd be given Fick's law. And your diffusion constant would also be given to you. Now, you should also know the size. You should also know a little bit about the size of cells in osmosis from biology. And because of time, I'm going to have to stop the screencast here, and we'll tack this on to the last screencast.